you. I first would like to clarify a little bit last thing I said yesterday. So I was speaking about S-unit equation, x plus y plus z1. S-units. Basically, we can view x, y, z as coordinates in GM QM3 and consider the projection to P2, which is very simply defined by associating to the vector point, this projective point. And the surface defined by this linear equation projects to P2 in such a way that the image of P is the complement of 4 lines in general projection, in general position. GM3 projects to P2 minus 3 lines, which is a GM square, and V is sent into the complement of a 4th line. Then you draw the picture, you think of the complement in the plane of this configuration of lines. There are clearly 3 curves which are isomorphic to GM as algebraic varieties. And this is connected with the fact that the solution to these equations form a finite sporadic set, which depends on the number field and S, plus 3 infinite families, which are given by, for instance, Z equals 1 and X plus Y equals 0. And these are represented by this line. Okay, now I want to give generalization of the S-unit theorem in 2 directions. First of all, we can replace O as star, so the group of S units in a number field, by any finitely generated multiplicative group, always in characteristic 0. This is achieved by a specialization argument. General philosophy is that if transcendental quantities arise in Diophantine equations, then it is easier to solve. It is easier to prove the finiteness or degeneracy of solutions. And second direction, extend to nonlinear equations. To be solved in S units, or more generally, in a finitely generated multiplicative group. And this is obtained in a very easy way, viewing any polynomial in any number of variables as a sum of monomials. Monomials are sum of or linear combinations of monomials. And so, first of all, one can enlarge the multiplicative group so to achieve that all the coefficients are in this group. And so each term of the polynomial, while when calculated in elements of this finitely generated group, still is in this finitely generated group. So finally, we reduce to an S unit equations in several, in many more variables, which depends on the degree of the polynomial. So finally, we can consider an algebraic variety inside multiplicative group. Algebraic variety. And we can intersect, well, we can take delta, a finitely generated group. And consider E. So E delta D. And general theorem is due to Laurent, Michel Laurent. That's the Zariski closure. Set D intersect delta Dn is a finite union of translates of algebraic tori contained in D. It's a finitely generated multiplicative group delta is a subgroup of a field, a subgroup of C star, and delta to the n is a set of points. Yes, one could also consider a subgroup of Gm to the n, which is not a product, but anyway, it would be contained in a product. And so finally, this is an application of the Schmidt's subspace theorem, which I presented yesterday. And this will be the first tool to prove our theorem. This is the Diophantine part. And then the second tool is a theorem by Prasad and Rapinchuk on generic elements in a subgroup, Zariski-dense subgroup of the semi-simple group. So let's consider an algebraic group G side GLN. G is semi-simple. Zariski-dense finitely. Yes. But anyway, then I have to use a field which is finitely generated, so it will be automatically. So a K, a finitely generated field, and gamma is a subgroup of G of K. So we can consider the generic characteristic polynomial corresponding to the representation of G as subgroup GLN. So PGX is determinant P minus X identity. And this is polynomial with coefficient in the ring of regular functions of the group G. And the theorem says that gamma contains Zariski-dense set of semi-simple elements gamma such that Galois group over K of the characteristic polynomial is the same as the generic one. It's the Galois group of this polynomial over the function fields of G, and moreover, gamma, the subgroup generated by gamma, stands in its centralizer which is a torus. And now let us start the proof of the theorem of bounded generation. So first of all, it's a group which is bounded generated by simple. And the first thing we showed is that the Zariski closure, the connected component, cannot be semi-simple. This will be the first step. And now consider, so this is the statement. Now consider.
Wait, Pietro, what's gamma here? What's the assumptions on gamma?
Gamma is a linear group. Well, the ultimate goal is proving the theorem with Rapinchuk, Ren, and Zamner, which states that if a linear group gamma inside GLN, okay, is bounded generated by semi-simple element, then it is virtually abelian. This is the main result. And so as a first step, I proved that its Zariski closure is cannot be semi-simple. And it will follow formally that it will be solvable, and then another argument is needed to prove it is abelian. So first of all, considering finite index subgroup, we can suppose that the Zariski closure equals G is connected. Now let U1, UT in any order be the eigenvalues of gamma 1, gamma R, and let L be the field generated over K by these complex numbers, and let delta inside L star is such that be the group generated, multiplicative group generated by the eigenvalues. Now we can apply the Rapinchuk theorem in a slightly longer form. It follows formally. Rapinchuk and find gamma, which is semi-simple. And such that gamma contains an element lambda such that no power of lambda belongs to delta outside lambda to be 0. And to obtain this, we exploit Galois genericity. I'll just give a couple of examples. So G is SLN, then the Galois group over of the polynomial over the G is full symmetric group Sn. And if n is at least 4, this cannot be the Galois group of a Kummer extension, of an extension obtained by taking groups. So, so first of all, lambda cannot belong to delta. So this lambda does not belong to delta because the Galois group is not trivial. And if lambda to the m belongs to delta, then the Galois group would be either cyclic of order m or diedral if a finitely generated group, the group generated by the. Yes. Oh, I forgot to say, sorry. Yeah, we applied Prasad Rapinchuk with the over the field L. So over the field L. So of course. So lambda cannot belong to L because it generates an extension with non-trivial Galois group. And this extension cannot be obtained by yes, certainly. We apply with L. So if n is large, it works. If n equals 2, for instance, then S2 is Z modulo 2Z. But if gamma has an irrational eigenvalues, that's also its conjugate. And if it is a square root, its conjugate, it's opposite. But then the trace is 0. And since we dispose of a Zariski-dense set of possible generic elements, we can suppose that the trace is non-zero. So we avoid also this case. I give another example. G equals SO3. So the generic polynomial has one root, which is equal to 1, and then it's irreducible over L out G. And so when specialized to a generic element, it will be irreducible over L. So again, gamma will have 3 eigenvalues. One is rational, the other 2 are irrationals, and I use the same trick. So the trace in this case would be 1 if this is so we can always suppose that lambda does not belong to L. Now, Now, after diagonalizing, and suppose that gamma is lambda and then something. So gamma to the n has an entry equals to lambda to the n. And since gamma to the n can be written as R, and since the gamma I are semi-simple, the powers of each gamma I is parameterized by purely exponential polynomials. Polynomials in U1, UR, so is the product. So we obtain lambda dn equals an expression this form for a purely exponential polynomial. And in other words, this is an ordinary polynomial calculated in R equal this time, where G is a polynomial. Now let us consider the variety V included in Gm to the R plus 1, defined by the equations y equals G of x1 at R. So each point lambda to the n, u1 to the n1, ur to the nr lies in V. And it's a point whose coordinates lie in a finitely generated group. Well, we extend delta so that yeah. Now, obtain yes. Yes. Yes, yes. Yes, yesterday I explained that yes, yes. Gamma, the first gamma is diagonalized. And now, since there are infinitely many solutions, there exist torus of dimension at least 1 and psi m to the r plus 1 such that psi p is contained in V and contains a Zariski-dense set solutions. Oh, sorry, this is a priori L-bar because diagonalizing gamma makes use of other coefficients. Yes, that's a problem. Otherwise, it will be. Is a purely exponential polynomial, which means an ordinary polynomial calculated in expression of this kind. So in terms of n1 and r, it's exponential. It's a linear combination of exponential functions in n variables. Now, well, we can replace L bar by a finite extension, but anyway. Yes, but anyway, here I have finitely many elements, so they generate, well, a polynomial has finitely many coefficients. So a polynomial has finitely many coefficients. So now I apply Laurent theorem, which says that there is a translate of a torus containing V, on which the solutions are Zariski-dense. And now, a torus is these intersections of toric hypersurfaces, and a toric hypersurface in Gm to the r plus 1 is defined by equations of the form yk0 equals x1 to the k1 r to the kr, or k0 k1 kr z to the r plus 1, not all 0. So T will be defined by a system of equations of that kind. And now I claim that, yes? Well, for a finite extension of L. So let's call L prime finite. No, gamma, small gamma is small gamma is defined over L. It's coming from your theorem, but when I diagonalize, I need to work over a finite extension L prime. No, I choose gamma depending on L. And then when I have gamma, I diagonalize gamma. So gamma is not this one, it's conjugate over L bar to this one. But gamma is defined over L. Okay. So finally, I obtain this situation. And now a torus is defined by finitely many equations of this kind, and a translate of a torus will be defined by an equation of that kind with a constant possibly different from 1. So first things, exclude that in every equation k0 equals 0. So if this were the case, then the involved equations would be only in x1, xr. But then since y is non-constant, function of x1, xr, and is non-constant and remains non-constant over T, because the over T there are infinitely many solutions, infinitely many points, where lambda n is a function of the last three coordinates. Y is lambda n is a function of the others, and we have infinitely many n. So actually, in this different equation, for every n, there exists n1 and r. So not only there are infinitely many r plus 1 tuples, but the sequence of the first coordinate n is injective. So, so this is excluded. It's excluded because over the translate of T. So over the translate of T, we are supposing there are infinity solutions. Then there exist equations with A0 different from 0. But now just take two solutions to eliminate A. So we have A lambda n equals U1 to the N1 U R to the NR, and A lambda n prime with n different from n prime equals the same thing with other exponents. And then taking the quotients, we obtain that lambda n minus n prime belongs to delta, which is executed. So we have proved that G cannot be semi-simple. Then by standard technique, we consider the quotient modulo the radical. The image of gamma is still Zariski-dense, and the image of semi-simple elements are still semi-simple. So it turns out that this cannot be semi-simple, so it's trivial, and then this means that G is solvable. And to prove that that gamma is indeed virtually abelian, we use another Diophantine argument coming from a work in progress with same author plus Julian de Mello. Well, let's see. So we prove that gamma, this gamma here is solvable. Well, it's Zariski-dense of gamma is solvable. So and take the quotients by important. This is torus. The first case, gamma contains only semi-simple elements. Then the projection is injective, and so it is abelian. And second case, gamma contains no semi-simple elements. In this case, we have to use subspace theorem in its full form, not only via its corollary on S-unit equation theory. So the idea is that gamma to the n, after conjugation, there exists a gamma and gamma, a non-semi-simple, such that gamma to the n as one of the A0, G0 of n is a polynomial. So raising to the power a non-semi-simple element, there appear also polynomial functions. And so, but again, this polynomial must be, for every n, it must be equal to a purely exponential polynomial, or sum of units, a polynomial in the units. And now, the kind of Diophantine approximation we used is statement that the value set of such a function is much sparser than the value set of a polynomial function. For instance, if this were just one exponential function, 2 to the n, it's clear that does not exist a polynomial, such a non-constant polynomial, such that all its values are powers of 2, for instance, because the power of 2 go much more rapid. And if we consider again the proof that 2 to the a minus 3 to the b equals constant has only finitely many solutions, this can be stated as the fact that this difference tends to infinity in any infinite sequence of A, B. That's exactly the same thing. But the proof of this theory of finiteness of these Diophantine equations is constant. For every constant, this equation has only finitely many solutions. Solutions A, B in natural numbers. So this difference tends to infinity. But the proof which I gave yesterday also shows that this difference is for every epsilon larger than a constant depending on epsilon by the maximum of 2 to the a, 3 to the b, the 1 minus epsilon. So it tends to infinity very rapidly. In particular, no polynomial can have, no non-constant polynomial can have all its values at integer points equal to an expression of the form 2 to the a minus 3 to the b. And this idea shows that this cannot hold for every n. So it cannot be true that for every n there exists n1 and k with this property. And the last result, which can be proved by this using these ideas, is that for a linear group, gamma over a field of characteristic 0, the following are equivalent. First, gamma say, gamma is parameterized by purely exponential polynomials. So gamma is anisotropic, so it contains no, it contains only semi-simple elements. And is boundedly generated. And three, the Zariski closure, magnetic component is a torus. And gamma is finitely generated. So the three conditions are. And that's all. Purely exponential polynomial. So expression, linear combinations of expression of the form U1 to the n, UR to the n, N1 and R. Linear combination. Yes, only things. So thank you very much for the attention, and thank you again for the organizer.
Questions for the speaker?
Hi, it's a technical question. How did you exclude the case where kappa 0 or k0 is 0 in your argument? That you just erased it?
Because the torus is defined in this way. Well, sorry, the variety, the algebraic variety is defined in this way. Y is a function of the other coordinates. And we consider a translate of the torus contained in V. So that on this set, the equation still holds. And also, on this set, there are infinitely many points of this kind. And since lambda n vary, lambda cannot be lambda to the n, so y cannot be a constant function on this subset.
Any other questions? Maybe I have a quick philosophical question. So when you set out on this path, did you expect to prove boundedly generated or not prove boundedly generated, or was it just we'll see how
I expected a proof. For, from a Diophantine point of view, it's not surprising.
Well, I think it's surprising for many of us here. So let's thank Pietro once again for the lecture.